Okay, so what I wanted to do today is talk a little bit more about monoinvariants. We have actually seen monoinvariants already this semester in one of the homework problems. Does anybody know which homework problem involved monoinvariants or could be solved using monoinvariants? So, any thoughts?
In sort of a cheesy way, the Lagrange problem.
I was thinking of a different one than the Lagrange, yes.
So maybe the tiling one?
The tiling one it could in some sense involve a monoinvariant. So here's a related tiling problem. All right, so here is a 6x6 chessboard, and I'm going to delete the two corners. In the interest of time, I'm not going to draw the 8x8. It just takes too long. You can do it on the 8x8. All right, and I want to tile it with 1x2 dominoes.
What's 7 by 7?
Oh, is it? All right, 1, 2, 3, 4, 5, 6. All right, let's go up to the 8x8. All right. So now we have an 8x8. Oh, no. And I have to go down one, right? One of those nights. Oh, it's daytime, right? All right. There you go. I know, I was going to say, yeah, we don't have any natural lighting. All right. Is this now roughly an 8x8 chessboard? And I want to tile it with 1x2. So the question is, how do you try to attack a problem like this? What should you do first? Smaller cases, okay? What's the smallest case you can consider? So if we try to do a 1x1, there's nothing to do. So we try to do a 2x2. All right, we remove this. All right, how many ways are there to tile this? None. All right, passing notes in class.
She wanted to know about convergence.
So if we now look at 3x3, let's see, would it be 1, 2,
No.
any way to do it?
It doesn't make any sense because you have an odd number.
So here, we know immediately it's false. We have an odd number of squares. And this is why I did not want to stay at 7x7. Right? So if I do any odd board by odd board, there is no way to tile it. You're just using 1x2 squares. Right? What if we now go to 4x4? So 1, 2, 3, 1, 2, 3. Now it's not so clear as to whether or not there's a way or not a way to do it. So after exhaustive study, let's pretend we found that there were no ways to do it. Okay? All the odd cases are handled easily, so now we're down to just the even cases. So how is this like a monoinvariant? So the way these monoinvariants work is given an object, you need to associate a quantity to it whose magnitude is either always, is only moving possibly in one direction. It's either staying the same and getting larger, or it's staying the same and getting smaller, but it doesn't go up, down. So I want to associate something to this.
Number of ways to tile.
I could do that, but that's going to be hard. Now, this is not a well-drawn chessboard, right? There are many reasons why this is not a well-drawn chessboard. But what is different between a chessboard and this? When you picture a chessboard in your mind, what do you see? Describe it. Yeah. You see two colors. So let's color things in. Oh, now this is interesting. I've lost two corners that are the same color. When you put a domino down, no matter how you put it, you have to get one black and one white square. So every time you place a domino, you remove one white square, you remove one black square. So the monoinvariant is the number of black squares minus the number of white squares. And to be honest, I have no idea in this picture which are the black squares and which are the white squares. This is the problem of using white chalk on a blackboard. But whatever this quantity is, which do you want, we'll call these the white squares, the ones that are shaded in. So what is this difference going to equal? No, not 0.
Oh, okay.
Negative 2.
Negative 2. Because we always have 2 more white squares than black squares. So every time I put down a tile, I'm going to lose a black square, I'm going to lose a white square. Does it change this quantity? No. So you can imagine putting down the tiles, the dominoes, one at a time. And at the end of the day, if you have a covering, you've now shown that negative 2 equals 0. Why? Because every domino when you put down, it's perfectly balanced with black and white. That's the only ways you can place them. So every time place a tile, decrease white by 1, decrease black by 1. If tile at end, you would need the number of black minus the number of white to equal 0. But this is constant. And so this is the power of looking at the monoinvariant. Actually, in this case, it's an invariant. It doesn't change at all. It's always negative 2. So to me, this is a phenomenal idea. The first time you see this, this is absolutely shocking. We don't have to look at all these possible configurations. We don't have to look at all the different ways to place tiles. It just can't happen. Now, what if we tried the odd case? Does the argument work in the odd case? Let's go back. So let's say what's going on here? So in this situation, we've thrown away 2 of the 9 squares. We have 7 squares left over. Is it possible that blacks and whites are evenly split? No. So instead of being negative 2, it's going to be either negative 1 or positive 1. So here, we'd get number of black minus the number of white is going to be negative 1. And again, it's impossible. So we can use the same proof in both cases. It's a little bit different. We have to have negative 1 or negative 2, but it's the same idea. The hard part of all of these problems is thinking of what is the right invariant. What is the right quantity to look at? The best way to figure it out is to do lots and lots of problems. The more you do, the easier it becomes. Okay? Most of you probably do not want to spend every waking moment doing math problems between now and when you die. Fortunately, it's only till the end of the semester, so it's not a problem. Okay? I'm not expecting you to do that, but if you really want this stuff to sink in, the more problems you do, the better it's going to be. I'm not going to overload you in terms of the problems I give you. I'm pointing you to resources. If you want to do more problems, if you want to talk to me, if you want to talk to the TA, if you want to talk to each other, that's great. I just want to give you a sense of what's out there and what kind of techniques. These are great ways to attack problems. The other thing which I like about this is introducing this additional structure on the board and the tiles, putting in these colors, and it really helps. So before we do more problems, I guess part of it is I want to use this as a springboard. So let's talk about research problems. How would you generalize this problem? Yes?
You could look at what happens when you take like an n by n board and just take out any two random tiles.
So if we take out two random tiles, what's the probability if we take out two random tiles that's colorable? We know that the random tiles have to be the same, have to be opposite colors. But how often can you take out two tiles and have it colorable? Is it possible to take out two tiles and have it colorable?
Yeah.
Yes. Which two tiles?
Just take two.
So if you take two neighbors, it should probably always be doable. Maybe not, but this should be, I think you'll be okay. If not, a little bit of a tweak. What else could we do? So one way to generalize this was to look at taking out just any two tiles. What else could we do?
Take out more than two tiles.
Could take out more than two tiles. What else could we do?
Add in tiles.
I'm sorry?
Add in more tiles.
So well, adding in tiles is the same as taking away more tiles from something else.
Use a different domino.
Use a different domino. How does the answer depend on the domino? What if I had a 1 by 3 domino? And let's assume we're in a case where at least the correct number of squares exists, so that the total number of places to tile is a multiple of 3. When will that be doable? So a whole slew of things you could do. And then it was like, well, how would I choose the coloring of the board? Maybe I would do things modulo 3. If I view this as maybe the point 0, 0, look at these as the center 0, 0, 1, 0, 2, 0, 3, 0, 1, 0, 1. And now I'm choosing my coloring based on the parity of x plus y. If x plus y is even, I don't color. If x plus y is odd, I do color. Maybe I do something now looking at things with remainders modulo 3. So if you want to try to create your own problem, try to come up with something along those lines. And that's the way you really learn a subject, is trying to create problems. Okay? All right, so there's a whole slew of problems. I chose 3 of them. 2 of them I made sure I knew how to do. 1 of them I made sure I do not know how to do. Okay, so you have n people, r rooms. Anybody look at this one?
Yeah.
Okay, so how do you remember the phrasing?
If there are people in more than one rooms, somebody always moves to a room with more people.
So this is where you have to be very careful in terms of how you phrase it. I want to say, if people in 2 rooms, someone moves from a room with fewer people to a room with more. Is this a good phrasing? I'm sorry? Well, if they're in 2 rooms, that's there could be people in more than 2 rooms. I mean, I'll put in at least. So if people are in at least 2 rooms, someone moves from one of the rooms that has fewer people to one of the rooms that has more people.
Do they know where all the other people are?
I'm sorry?
Do people know where the other people are?
Sure.
Okay.
They're Facebook friends. And people are constantly updating their status, in Bronfman B34, cool math going on, come on down. M&Ms. And then somebody else says, yeah, but colloquium at 1 p.m. 1:06. What's bad about this phrasing? What do you think the goal is? What do you think they want to happen as time elapses? Everyone ends up in the same room. So do you think that this phrasing is enough to make sure that everybody will end up in the same room? Or could there be a problem? Yes?
Maybe if the two rooms have an equal amount of people.
Yeah, what if we have 10 people, and then every other room has 0? You move from a room with fewer people to a room with more. There is no room with more people. So if this is the phrasing you use, you could be stuck in a situation like this. So if people are in at least 2 rooms, someone moves from a room with fewer or equal people to a room with more or equal. We have to put that in. So that if we're ever in a situation where all the rooms have the same number of people, then just somebody says, I'll move. And they'll move over to the next room. Now the problem is well defined. There's a much easier version of this problem. So right now, somebody gets up and moves to some room. How could I make this problem really easy? Move to the room with the most people, right? So if I do that, well then okay, whichever room has the most people, and if there's a tie in the first round, then after the first round there's going to be one room that has the most people, and it's just going to keep getting bigger and bigger and bigger, and everybody will end up in that room. So if I put that in, always move to the room with the most number of people, it's fine. So the question is, what is the right invariant, what is the right monoinvariant to look at for this problem? I know the way the notes solved this. I'm curious to see if we can find another one. Mm-hmm.
So for this problem, couldn't you have a case where there's, say, 10 people in the first room, 2 people in the other room, and people just switch off between the second and third rooms?
Okay, so we could go 10, and now what do we have?
2 and 2.
Well, if they switch, then this would become 3 and 1.
But what if the
No,
other
but the,
person's switching at the
person-
same time?
Some person moves from room 2 to room 3, some person moves from room 3 to room 2. So you still have 10, 2, 2 after every.
No. Only one person moves at a given moment.
Only one person.
Only one person moves.
Got it.
So you can't have multiple moving. It's a very polite group of people where they don't interrupt. So if you want to see the opposite, come to Dodd tomorrow at 5:30 with my kids. So only one person moves on a turn. So we have to figure out what should we have as the invariant.
Number of rooms that have more than one person. Have one or more. The number of rooms that are complete.
Number of peopled rooms? Is that what you're saying?
The number of rooms that are empty.
Number of rooms that are empty? Okay, that's, in some sense that's the same as the number of peopled rooms. I just like saying the word peopled.
Okay.
So one possibility is the number of peopled rooms Another suggestion.
How about like the maximum room never gets smaller?
All right, the number in the most populous room. So right now, I do not care if these things work. I just want suggestions.
Sorry, what's the question again? Like how many?
Oh, the question, the conjecture is that eventually everybody ends up in the same room.
Oh, okay. So we're just saying.
We're trying to find what would be good monoinvariants or invariants.
I mean, you can use the number of rooms that have at least like n divided by r people in them. So like who have at least the average number of people per room in there.
Okay, number of rooms with at least the average number of people per room. Other suggestions. The book suggested the sum of squares of people in the rooms. So I deliberately do not care about going straight to the jugular, going straight to a solution that works. The hardest part of these problems is figuring out which quantities are worth studying. And so I think it's worthwhile just talking as a class and trying to think which ones will work, which ones will not work, why will they work, why will they not work. Some of them might work but might be harder. So I'll start with number 4. Sum of squares of people. So imagine we have n1, n2, nr, and somebody moves. Without loss of generality, let's assume somebody moves from room n2 to from room 2 to room 1. So we now have n1 plus 1, n2 minus 1, nr. And I might as well assume that the rooms are ordered like this. So this is using, without loss of generality, freely all over the place. At some moment in time, do I really care about the room labels? So what I'm going to constantly do is I'll constantly maybe rename the rooms. Whichever room has the most people in it, it's room 1. If a couple of rooms have the most number of people, fine. We'll just randomly assign labels to them. And that's why I have to use greater than or equal to's. And so somebody moves from a room with fewer people to more people. Now, as soon as I do something like this, now I've got to be a little bit careful. This is not the most general case. I could have somebody moving from here. And so really, I would have to be a little bit more careful, and I would have to have maybe NL minus 1. Because it may not be the adjacent one. So let's look at what we were before. We had n1 squared plus nl squared. And then after the movement, we had n1 plus 1 squared, nl minus 1 squared. So the change after minus before, so the n1 squareds cancel. I get 2n1 plus 1. The nl squareds cancel, and I get a minus 2nl minus 1. And what does that sum equal? It's going to be 2n1 minus nl. And what can you tell me about this? It's at least 0. So we've just shown that this is a monoinvariant. If it moves, it can only move up. How many possibilities are there? A finite number. I'm coming off a really technical linear programming class today where we had potentially 50,000 choose 10,000. It's a huge number, but it's a finite number. There are only finitely many possibilities. We start off with a fixed number of people, a fixed number of rooms. You look at all the possible configurations. So this quantity is non-decreasing. So what's going to happen as time goes on? Yes?
Well, I think in the expansion of NL minus 1 squared, the 1 plus 1.
Oh, you're right. I'm sorry, you're right. I was about to say, you're right. They actually reinforce. Thank you. Even better. Thank you. Much better. Thank you. Yes. So it's strictly greater than 0. So as long as, and now as long as we have 2 rooms with people, it increases. As long as at least 2 populated rooms increases. Excellent. So what's going to happen?
At this point, it's really easy because we just have to show that the upper bound happens when one room has all the people, and so it's bounded and increasing.
Right. And so imagine you didn't have everybody in one room. And then imagine we've also hit the maximum possible value. Well, if we have people in 2 different rooms, then we can make it larger. So we can't have people in 2 different rooms and be at the maximum. As long as 2 different rooms are populated, we can do this and get to a larger value. So the maximum has to occur when everybody's in 1 room. That's the monoinvariant. And so you don't know which room people are going to. They don't have to go to the most popular room. So this was a very interesting choice. And again, I will admit, when I was looking at the notes for today, I happened to read that it said, look at the sum of the squares of the number of people. That's an inspired choice for a problem like this. That's not an easy thing to see. So I want to make sure, is everybody on board with this before we start looking at some of the other ones, which I think are more natural? All right, so let's look at some of the other conditions. We have the number of peopled rooms. If we can eventually show a room gets empty, we win by induction. So that's one possibility with 1, is can we eventually show 1 room goes all the way down to 0 people. Another possibility is the number of people in the most populous room. Can the number of people in the most populous room ever go down? Why can't it go down?
If it's strictly the most populous room, then no one would move from that room by the rules.
But maybe you have this young whippersnapper coming up, and this room initially was not that exciting, but then people discovered, hey, this room is really cool. It's like the Blair Witch Project. You have this whispering campaign going on, more people start going to see it, and pretty soon this new room becomes the most popular room. And nobody's in Bronfman B34 doing mathematics anymore. They're watching movies from when I was in grad school. Why does that not contradict this being an invariant? Good. I'm not saying which room is the most popular. If someone else is going to supplant me, they can only move up by 1 at a given moment. And I could move down by 1. If I'm the most populous room, am I going to move down? No. So there's another room, it's climbing. Maybe I move up a little bit, they move up, and eventually they tie me. And now at that point, they could either gain somebody from somebody else, or they could gain somebody from me. And I'm no longer the most populous room. But the number of people in the most populous room is never going to go down. This would be a monoinvariant, the number of people in the most populous room. The problem is, do we know that it's going to increase? So we would need to show that eventually somebody goes into the most populous room. And so I think we could make this work, but I think it's going to be a lot more work than the sum of squares approach. So should we try to make that work? That eventually, if we use the monoinvariant, the number of people in the most populous room, that will lead to a solution. This is a chance to vote. Loud voice wins. Does anybody want to see that? All right, nobody wants to see that, so we will not do that. So if you want, try to see if you could make this work. It is going to be a little bit more involved. You're going to have to then say, well, if nobody ever enters, if it never increases, if it's always strictly constant, there's going to be issues. The last one was the number of rooms with at least the average number of people per room. So I'm not quite sure how to make this one work. It's a good thing to look at. This is reminiscent of what?
So my idea when I was thinking of that one is to look at, you could basically just say that we're going to look at the most difficult case.
Okay.
So the most difficult case is when the room with the most people, like the amount of people in that increases the most slowly.
Okay.
So whenever given the option, people move into a room that's not the most populous room. And so gradually the rooms with like at least the average number of people would like get smaller and smaller and smaller, and eventually just be left with the 1.
In some sense, because are you going to eventually be arguing that some rooms will become empty?
Yeah.
Okay. If you're going to go along those lines, I think you might be able to make 3 work, but it's going to take a lot more work to make 3 work. So I think of all the approaches, I think 4 is the easiest. I think 2 might be the second easiest. The number of peopled rooms. If we can show that the number of peopled rooms eventually decreases, that's very similar to your average approach. Is that if the number of peopled rooms is constant and then eventually gets smaller, then eventually everybody has to end up in the same room. Comment or?
Could you potentially use like the well-ordering principle and say that there must be a room with minimal people in it, and by our rules that room must eventually become empty?
With a little bit more work, because then you would have the rooms above it, and the rooms above it would always be losing people. So the number of people in those rooms would have to be getting lower, and eventually someone would have to fall down to this level, and then it couldn't get any lower. And then another room would fall down to that population, and then another one. And then eventually all but one rooms would be at this level, the other one would be the highest. Where's this going to get a room from? It's going to get a room from there. So I like the idea of saying, imagine that there is a room with a minimal number of people and it's not 0. Then if you had such a room, eventually you would have to take someone from either that room or another room with that many people. And that argument would work, but it's not as easy to write. And that's one of the difficulties. One of the nice things is when you become a professional mathematician, you no longer actually write down the details in papers. And you just say, one can easily see that clearly, obviously it follows from, and you just keep going. But in stuff like this, especially on the Putnam, you have to write things out in great detail at times. Okay. If there are no questions on this, let me just say first the homework problem that was similar to this. Any other guesses as to which homework problem I'm thinking of? So let's revisit a to the a, b to the b, c to the c, greater than or equal to a to the b, b to the c, c to the a. And the way I proved it was saying, well, look, we're going to assume a less than or equal to b, less than or equal to c. They're all greater than or equal to 0. We can't assume anything about their sums or their products. But what we can do is we can move factors of c and replace factors of c with factors of a. It's easiest if everything's an integer. And I can just move full powers. But I can replace partly. And so this is very similar to this monoinvariant. Which would you rather have? A raised to the cth power or c raised to the cth power? Which is going to give you a bigger number? C to the c. And so if I start making trades, so when I wrote up the solution here, I wrote it as a to the a, b to the b, c to the c, minus b plus, one does I think, c plus b minus a minus b minus a. Okay, so the exponent of c is still c. But if I now replace the c to the b minus a with an a to the b minus a, I've gone down as long as a is not equal to c. And so this would then be greater than or equal to a to the a plus b minus a, b to the b, c to the c minus b minus a. Right? And so I've just replaced c with a. That's not a good trade. And now what would I do? This now gives me a to the b. So I have a to the b, b to the b, c to the c minus b minus a. I want to have b to the c. So how much do I have to add to the exponent? I have to add c minus b. So then I subtract c minus b. And that will give me a to the b, b to the b plus c minus b, c to the c minus b minus a minus c minus b. And when I do this, I get c minus b plus a minus c plus b, so I get c to the a. And so this is another way to look at this problem. Related to this is, whole types of inequalities. So they'll often give you, have some positive numbers. Now the only thing is, when I'm looking at this, do I have to be careful at all about the sizes of anything? I really want to just assume all A, B, and C are at least 1. Which would you rather have, x or x squared dollars?
X squared dollars are integer units.
Yeah, if they're in integer units, if I have a quarter, would you rather have a quarter or a 16th? You'd rather have the quarter. So you've got to be a little bit careful that sometimes the higher exponent could make things smaller. So in problems like this, you might often have the assumption that A, B, and C are at least 1, or they're positive integers, or something along those lines. One of the related inequalities is you have a sequence of numbers 0 less than equal to x1 less than equal to x2 less than equal to xn, 0 less than equal to y1 less than equal to yn, then x1, y1 plus xn, yn. How do you think that compares? I want to compare this to, say, x1, y sigma 1 plus x2, y sigma 2 plus xn, y sigma n. So I'm just shuffling the indices. I'm looking at, there's n factorial ways to shuffle the indices. Choose one of them. So maybe I have x1, y4 plus x2, y3 plus x3, y9. I don't care. Which do you think is larger? This one or this one? The first one. You have the two large numbers hitting each other. So this should be the largest possibility. Right? What do you think the smallest thing would be? Maybe going in the inverse. Maybe having x1 hit yn and y1 hitting xn. Maybe going backwards like this to try to minimize how much you can get from the large stuff. So there's inequalities like this that you can prove using these monoinvariant ideas. It's very similar to that inequality. It's great ways of ordering things. All right, so the next one, I'm not quite sure why they put it in the monoinvariant, but maybe you can tell me a way to view this in a monovariant way and not just another calculation. So we're going to play a tournament with n teams. And the teams will be playing each other in games of 2. So n teams, games of 2, if odd number at any point, randomly give a bye. So if we have 15 teams, we'll get 7 games involving 2 teams, and one team just lucks out and gets a bye. And you keep doing this until only one team remains. Okay? Once you get a loss, you're dead. One loss and out. How many games are played until we get a champion?
By loss of any of the games instead of 2.
Well, if we have 15 teams, we have 7 games going on. Each game involves 2 teams. There will be 7 losers. And
I thought you said matches of 2.
match of 2, games of 2.
So there has to be a winner.
Yes.
There are no ties.
Yes. This is still Bud Selig's Major League Baseball, where no game will end in a tie, because that is one of the worst things that could happen. There's just not enough time to go into why having a baseball game ending in a tie is bad. These games will be played until there is a winner. No draws are allowed. somebody wins, somebody loses. How many games must be played before the tournament is over? Well, I mean, if I have 15 teams, I can't play everybody at the same time. So one team just lucks out. So we can say, whichever team has, a mascot that occurs first in alphabetical order gets the bye. It doesn't have to play. You automatically advance. So I mean, let's say we have n equals 8 teams. So I could have A, B play, C, D play, E, F play, G, H play. And see, everything matches perfectly. You'll see, you often see brackets like this. And so let's say A wins here, D wins here, G wins here, and F wins here. Now they play and they get a winner. And now you have A plays G. And not surprisingly, A wins. So in this case, things were complete. If, however, we didn't have H, there wouldn't be a game here. G would just automatically advance to this round, and we just wouldn't have that game.
One thing that we can already see is that when there's a bye, that immediately resets it to be just even, numbers of teams right afterwards.
Correct.
So if there is an odd number of teams, we only have to worry about that for the first round.
Well, we could start off with 31 teams. One team gets a bye. So we have, maybe 31 is not a good number. Let's do 29 teams. So one team gets a bye. So we have 28 games going on. Those 28 games give us 14 winners, plus the one over here, that gives us 15. Right? So the 29, we have 28 plus 1. So this is going to be 14 games. And this is going to be 1 bye. And so unfortunately, we start off with an odd number. We in some sense became even with that bye coming along, but then we quickly became odd again.
So kind of going off of what you said, you can kind of sandwich things. So if you have 2 to the k, you have k games.
Okay.
And if you have 2 to the k plus 1, then you have k plus 1 games. So for anything in between 2 to the k and 2 to the k plus 1, if you can show that the number of games is
So this is k games, and this is k plus 1 games. And so we're somewhere in between.
I think that the number of games, I think there are going to be more games in general. Right? If you have 2 to the k, then you pair off people in each round. You have 2 to the k minus 1 games played in that round.
Right, you're right. It is actually.
Oh, maybe I meant
Yes.
rounds.
I think you meant rounds.
Right.
Yes.
Oops.
Yes. And so this would be 2 to the. How many games would this be?
K, and then minus 1, but the minus 1 is not in the next round.
It would be 2 to the k minus 1 over here. And this would be 2.
We may want to do it in rounds. I'm not saying this is the right way.
Well, there is an elegant one-line solution to this problem.
Every game gets rid of one team.
Every game gets rid of one team. Right? Every time we have a game, someone is killed. I'm sorry, they lose. Sorry. Someone loses, they're gone. How many games is it going to take to eliminate n minus 1 teams? N minus 1 games. So the number of games played is 1 less. Number of games is number of teams minus 1, as each game eliminates a team. So what I like about this is this shows you how the monoinvariants, the invariants, can save you from doing very long, tedious algebra. I maybe tried to deliberately color you by having you think in terms of rounds and stuff like that by drawing this on the board. I apologize, half-heartedly. Okay? But the question is, what's the right thing to associate to a problem like this? And if you think about it, what are we trying to do? We're trying to figure out how many games are played. What does a game do? A game gives us a winner and a loser. And once we have a loser, the loser is put off. Do we care how many games a specific team wins? We just care how many games are played. So, I mean, you could ask the related question, what is the maximum number of games a specific team plays before a winner is declared? That's very different. Okay? So the question is, what would you call the monoinvariant here? I might call it maybe number of teams left after, and every time you play a game, you lose one team. And the number of teams left has to go all the way down to 0, so every time you play a game, you lose a team. And what you want to do is you don't want to keep track of the number of games in some format like this. You want to say every time 2 teams play, 1 team is killed. And so it adds up eventually to n-1 games. Any questions about this? So I'll pose just one more problem. This is the problem I didn't do, so that if people want to, we can discuss this on Friday. If there are other things you want, if there are other topics you want to see, email me. I'm happy to discuss them on Friday. And so I have some ideas, but I deliberately did not finish solving this one. So you have n cards, n1, n2, C1, C2, Cn. If not 1, reorder the first C1 cards. So imagine I have 3, 4, we're running out of time, 2, 1, 5. So my first card is not 1, so I reorder the first 3 cards. So it becomes 2, 4, 3, 1, 5. Now first card is not a 1, so I reorder the first 2 cards, becomes 4, 2, 3, 1, 5. First card is not a 1, so I reorder the first 4 cards, 1, 3, 2, 4, 5. And what do you notice? One is the first card. What do you think the conjecture is? You'll always end up with 1 as the first card. So I have not finished solving this one, but if people want to, this would be a fun problem to talk about. It's in the monoinvariant section, so probably some monoinvariant. There's a couple of natural ones to consider. And that's what I like about this, is there's a lot of different things you could try. Which is the one that's going to work? Okay.